This conference will now be recorded.
Okay, so this is the December 8th, Wednesday morning IQ Pump Agricultural VFD training class. And we're going to talk about sensors, vibrations, pressure sensors, vibration sensors, and we're going to get into a discussion about short circuit protection. So I'm going to focus on one sensor because they're very illustrative of one pressure sensor because it's illustrative of pretty much the entire market. Again, form factors are the same, pipe taps are the same to standard, and on some of the European manufacturers, you just got to be sure that you order the NPT that you want and not some DIN standard, because then of course you're not going to have a good interface mechanically. But all the sensors are 24 volt power, 2 wire typically. Some of them have instead of just the analog output coming back, typically 4 to 20 milliamp, that's relative to the pressure range of the sensor. You also have some other conductors coming out of the sensor for switches that can be programmed to close digitally at certain pressure levels, such as high-low. There are sensors also that are capable of a serial communication output, which means you can hook them up to a network. And in the ultimate configuration, these sensors can be wireless. And what I mean by wireless is you install the sensor out in the field, you install it to a transmitter, typically on an RF frequency, and that transmitter will transmit the data back to a receiver that can be line of sight as much as a half mile away. And these are non-licensed frequencies. These are also what they call spread spectrum frequency hopping technology, so they're relatively immune to interference. And they're a very convenient way to avoid running pipe and wire all over the back 40 of your particular outdoor installation. So let's focus a little bit on the sensor itself. And they all pretty much come out in this form factor. It's basically a stainless steel barrel. Make sure you get a type 316. There are some less expensive sensors out there in type 304. Not as good a grade of stainless steel, tend to corrode after a while. Type 316 is a very robust anti-corrosion steel. These sensors are field installable outdoors, no issues. And the main bugaboo about these sensors is making sure that the field wiring is secure, number one. And number two, that you bear in mind that the signal is a low voltage, low current signal, certainly subject to some interference, especially if you're using it in the neighborhood of a variable frequency drive, in which case the variable frequency drive is probably the worst case noise source. And that sort of noise overlay from the 700 volt spikes on the output of the VFD tends to disrupt the amplitude of the pressure sensor signal coming back. So a good shielded cable, and we've done this in other classes, but I recommend for control wiring using a shielded cable that is both foil and what is the name of that other? It's sort of like a weave. Both of those shield methods on one cable give you the maximum signal protection. The foil is standard on most low-cost shielded cable. The weave that goes around that is available on the more costly cables, and the weave is important because It has a lot of surface area as opposed to the foil because it's a weave of many small filaments, and has a better Litz effect property in terms of syncing high frequency noise to the ground plane that the shield is connected to, if you install it properly. So we have a best practices presentation that is part of this class series that shows you how to install those shielded cables properly using the tool to strip 1 inch off of the outer jacket, typically midstream on the cable, clamping it to a ground clamp, and then running the shield right up to the termination points on whatever device you're using to read the signal from the pressure sensor. Drop me a line and I can send that to you. This is a good point to do some housekeeping notes. I am working with our IT guy at Western Automation, and we're going to put up a landing page for all the presentations and the materials. I've been really bad about that, and I apologize, mainly because of my ignorance of how to do that sort of thing. Tried Dropbox and a bunch of other things, and it didn't really work very well. The GoToMeeting has a utility to do that, but they time you out, and unfortunately that means that it's time sensitive, and I wanted a more permanent installation. So we're working on that, and we should have that up after the holidays. Now, back to the sensor. The main issue that I have with the sensors is the fact that the field wiring is, in my opinion, a high-risk issue in terms of future problems. And that makes sense because the human intervention factor is always going to introduce some sort of risk in terms of the performance of a system. And we want to minimize that. We also want to make the job easy. And when you're out in a muddy field and you're doing an installation and you have a bunch of things on your mind, really it's not ideal to be messing around with a bunch of 18 gauge or 20 gauge wires with small connection points and a lot of potential ingress of dirt, etc. Plus the fact that you've got to seal it all up and make sure that it lasts the duration of the application, which is years. So the main reason I brought up the sensors today is to emphasize the point that we've had great success with sensors that come with pre-wired over-molded heads. I've noticed that is not normally the practice, at least in Southern California. I did a straw poll of my colleagues all the way up to the Northwest, and the fact is it's done differently in different areas. There are two over-molded technologies, and then of course the field wiring practice. And I'm going to say that I don't recommend the field wiring practice right off the bat, but I do recommend using pre-wired over-molded cables that basically screw in with a seal. It is an easy operation, it's relatively hard to make a mistake, and the over-molded connection on the sensor head itself is secure for years. So the sensor, type 316, stay away from the type 304 stainless stuff because that's basically the less expensive versions, and it doesn't hold up very well in terms of corrosion. Type 316 is a superior alloy. And then an over-molded, easy to install connection, no field wiring. That means by definition you're going to have flying leads. And you can buy the sensors and their over-molded connectors with flying leads out to 45 feet. We don't really want to make splices on signal cables. The cost of the cutaway wire versus the cost of basically the field time to install the field wiring, I think you're going to come out ahead buying the sensor with the 45 feet of cable. That adds about I think $6-7 to the cost of the overmolded head that connects to the sensor, and I don't think you're going to be able to field wire for $10-12 worth of labor. So, notwithstanding the reduced risk. So, what I want to show you is a couple of pictures of the overmolded heads, and let me see if I can. I'm just going to throw up a Word document here. Okay, so that worked pretty well. I don't know how this is going to scale up, but let's throw this up here. So this is a DIN head connector, and you'll see the spades right here. This is that's the head that goes on it. And you notice that this one is the field wireable version. You can see 4 spades going into the sensor head, and this allows for the power and signal return and a couple of digital outputs for pressure level, in addition to the analog that is proportional to the actual pressure itself. This is the business end of the sensor that gets inserted into the pipe. Now, this is what I recommend you use, because this is the overmolded version of that sensor. And you can see it's completely pre-wired, overmolded with a great seal. You basically screw this screw down into the stainless steel sensor body, and you're done. That, in my opinion, is a secure way of field wiring a sensor. Again, the cost of the flying leads is going to be a lot less than the cost of your labor that you're saving. And these type of connectors are available in inventory from the local distributors like Preferred Pump. This particular square head version is called the DIN connector. It is a European style connector. There's another type of connector that is called an M12. I'm just going to Google M12 so that you can see what it actually looks like. And so this is an M12 connector. Okay, where'd it go? Oh, my bandwidth is a little... And you can see this is actually a 5-pin connector. M12 meaning 12 millimeters in diameter. Again, a nice secure connection with an overmolded cable. You can buy them in a variety of lengths. This is the alternative to the DIN connector. In my opinion, both are equally secure, and it just depends on your preference and what is available through the distributor that you work with. So pressure sensors themselves, now that we've made the point on the oh, that's not what I wanted. Where am I here? Sorry, I got a little lost. I'm looking for the that's the vibration sensor. There it is. Okay, so in this product line, I just wanted to show you the wide variety. Here's your designation for the model, PT, and then here is the pressure range and scale, and you have all of these options. As I said, all the way up to, whoa, I didn't realize that, 14,500 PSI. Wow. Right here is the one that I typically use the most, and that is the 100, where is the 150 PSI? Is that Wait a minute. I think I've got the wrong page here. Yeah, there. Let's see. There it is, right there, the 150 PSIG. That's the one I typically use in the applications that I'm involved with. It's a very standard sensor, good availability. So in summation, field wire it, use a DIN overmolded connector with flying leads, shielded cable of course, and use an M12 overmolded connector with shielded leads. That's what we have to say about pressure sensors today. So let's move on to vibration sensors, and this is something I'd like to introduce as a method of remote sensing to get a pre-warning on potential mechanical problems. These pressure sensors are a peel and stick solution, literally. What we're talking about is some basic IIoT here, Industrial Internet of Things, where we want on the back 40 to monitor our pump, our drive shaft, our turbine housing to sense abnormal vibration. It's as easy as this. You install the sensor. There's a software configuration mode. There's a software configuration mode for everything these days. And this software configuration mode allows you to run the sensor for a certain period of time, typically days or a week, under normal operation, and the sensor will set itself up with a profile of what normal operation is, and then prompt you in the software to set up warning and fault trip limits. At this point, you have your sensor set up as your watchdog, and now it is just a matter of getting that signal back to where you want it to get it to. In an environment where you can hardwire, that's pretty easy. You just run a cable back to your PLC or whatever it is that you're using to read the signal from the pressure sensor. In the field, the ultimate configuration of this is what is shown here, and this is the sensor. It's about an inch square and about a third of an inch thick. It comes with or without these little LEDs to enunciate its status. This is going back to an RFI transmitter. This RFI transmitter basically will take the place of cable running back over hill and dale to a receiver that can then be wired directly into your PLC or whatever other programmable device you're using to sense the signals from the vibration sensor. And you will get the vibration data plus status on the pre-warning and fault levels that you've programmed into the little sensor in the field. A very nice setup, and we're talking probably less than $600 for the whole thing. And don't quote me on that. I'm not a price guy, but I think we're in that range. I mean, this isn't a $6,000 operation. Nowadays, the things that are available for remote installation wireless are quite cost effective because of the economy of scale of manufacturing so many of these things, because of the burgeoning IIoT hardware market, the Internet of Things devices. So, wireless being a big part of remote applications, ease of use, and the fact that you want to monitor vibration on that wellhead back across the lot, but you really don't want to run piping out to it. Well, you can't run much piping for $600. So basically, you get an RF signal coming back to this receiver. By the way, these are all IP67 components. They're basically peel and stick, leave them outside. And that's that. Illustrative of how the sensor is installed. There you go. It's literally a peel and stick. And there's your transmitter. So very easy to install, and a great way to bring back the data to a place where you can figure out that you're about to have a failure and get out there and repair it before you do. So, pressure sensors, vibration sensors. Hope this helped you. Let's move on to the final subject of the class today, and that will be a presentation by a colleague of mine at Yaskawa, and his name is Steve Perot. He's the senior product manager for Yaskawa back at the factory, which is in Chicago, and actually up in the northern Illinois near the Wisconsin border. And this presentation is about the replacement of the present UL 508 standard with the new standard, which is more numbers, of course.
Good morning, everyone, and thanks for joining today. Welcome to Yaskawa's Training Cafe Express. My name is Steve Pearl, and I'm the Chief Product Line Manager of Low Voltage Drives at Yaskawa America. First of all, Yaskawa wishes you and your family the absolute best during these unprecedented times of COVID-19. Continuing on with our purpose of being together today, this cafe session will be approximately 60 minutes, including questions, and is focused on short circuit protection of drives and related UL approval. Before we begin, however, let's cover just a few logistics. Okay,
we're going to skip over that.
Energy resulting from. So let's remember that because a system generally would consist of a transformer somewhere, possibly going from medium voltage to low voltage, and obviously the available short circuit or fault current right at the terminal of the transformers will be often very, very large. But at points further down the distribution system, that available fault current at a point in the system to which you would connect a load, such as a drive, that can be a lot different than the available fault current directly at the source. So let's all remember that available fault current.
One note here is that it is the installer's responsibility to determine the available fault current so that he can ensure that the SCCR rating of all of the equipment he is installing exceeds the available fault current. If he does not do this, there are some pretty significant liability issues associated with it. It is not the responsibility of the end user customer, be they an industrial plant or an individual on a winery, to determine and let the installer know that. If the installer is certified, and under the California code, that means he's got a contractor's license, a C10, I think it is, for electrical. He's been trained to understand the methods of determining what the available short circuit current is. Available fault current. This is, again, the responsibility of the installer.
So why should you care about it? First of all, electrical equipment has a wide range of ability to withstand that available fault current or energy resulting from. Okay? So improper selection and installation can result in extreme dangers such as arc flash events, even without opening an electrical panel. It can expel large amounts of energy that's deadly. The temperatures of this energy can be as high as 35,000 degrees, which is even hotter than the surface of the sun. It can throw projectiles, and it can cause normally grounded surfaces to become live. So how do you reduce the risk? By following the rules related to fault current. And the rules for fault current are established by the National Electric Codes, that being the NEC for the United States or the Canadian Electric Code for Canada. And it says that you must protect your branch circuit, which is typically the conductors up to the equipment. Now, this same protection, these devices, may often protect the equipment itself, but not always. And in cases where it doesn't actually protect the equipment, supplemental protection beyond what's protecting the wires is required. Okay, and then the equipment that's chosen, such as an electrical panel, needs to be chosen such that its withstand capability, or the short circuit current rating, is greater than or equal to the available fault current for the power that's connected to it. So as you can see on this panel here, the panel has a short circuit current rating of 14,000 amps. So obviously if there was more available fault current at where the power is connecting to this panel would not be sufficient, or the available fault current would somehow have to be reduced. Another important point here, when installing equipment, you absolutely must follow the equipment instructions, which will get into some of these details. Okay, next, let's talk about some typical scenarios for protecting drives. First, what does a drive by itself typically protect? Well, it typically protects itself during overload conditions. It typically protects itself during output short circuit conditions, that is, a short between the drive and the motor. The drive will protect itself against that kind of a condition. And then in addition to that, it's protecting the motor, that is a single motor connected to its output. But what does the drive typically not protect? It typically does not protect itself from short circuits in its own DC bus. It also typically does not protect external conductors or multiple motors connected to a single drive. There are a few exceptions to that, because there are some specialty and large drives that include short circuit protection for DC bus. In other words, built-in fuses. And an example of this would be the Escala U1000 matrix product. Another thing that happens to be going on with UL, which is a future thing and not yet a UL listed kind of situation, would be that they are considering the drive for being UL listed for protection of output conductors, but this is work in process. This is not available yet. So often, a separate device is typically required to completely protect the drive. And generically, we refer to those devices as overcurrent protective devices, for short, OCPD, which typically is a circuit breaker or a fuse. So let's look at a couple different drive protection scenarios. In the first case, we've got a feeder circuit that's feeding an overcurrent protective device that then is connected to the drive and to the motor. So in many cases, that overcurrent protective device is protecting the drive, and there's actually nothing else that's required. How do you know this? You know this by looking at the drive instructions and making sure that what's upstream is actually listed in the instructions for the drive. If it's not listed as UL protected device, then you have this other scenario that's going on where you have your overcurrent protective device that's protecting the conductors, but then you have to add, in order to completely protect the drive, an additional supplemental device. And again, in some cases that might be a breaker, but often when you have to add something, it's going to be fuses. Okay, so these are two sort of protection scenarios you can get into. Okay, so let's talk about this thing called short circuit current rating and amps interrupting capacity, because they are often confused. So a short circuit current rating is the maximum short circuit current a component or assembly can safely withstand. Okay, can safely withstand. These are very important words, and that's when protected by specific overcurrent protective devices. So the units that are normally associated with short circuit current rating are kiloamps or amps, never amps interrupting capacity, because again, these are applied to components or assemblies that are not the kind of devices that would open, such as a circuit breaker or a fuse. So SDCR is applicable to these kinds of devices. Okay, then we have amps interrupting capacity. So amps interrupting capacity is the maximum short circuit current that an overcurrent protective device itself can safely interrupt. You see on the left-hand side, SDCR is safely withstand. On the right-hand side is safely interrupt. Okay, and the amps interrupting capacity units are typically an AIC or KIAIC. So again, on the left-hand side, when we talk about assemblies or components such as drives or terminal blocks, things that aren't meant to interrupt the current, those are expressed in KA. And on the right-hand side, these devices are expressed in AIC because they are interrupting devices. So hopefully that clears up that. Next, let's talk about a system such as the enclosure that we saw in the previous picture. If we have a system such as a drive and an overcurrent protective device such as a breaker or a fuse, we can have situations where the ratings don't match. And this is often the case, most often the case. So let's take an example of a drive that has 100,000 amps SCCR, maximum capability, that has to be protected by something. Okay? And if we feed that with a circuit breaker or a fuse that has a 25,000 amps interrupting capacity, the combination of those two is limited to the weaker of the two. So that combination or that system would be limited to 25,000 amps SCCR. Okay, let's kind of look at a situation where they equal each other. So both devices, the overcurrent protective device and the driver, are both rated at 100,000 amps. In that case, the combination is actually rated at 100,000 amps. Now let's look at one where it's the opposite, where we have the overcurrent protective device that has an interrupting capability of 100,000 amps, but the drive only has a capability of 31,000 amps. In this case, the combination is 31,000 amps. So pretty easy to remember, right? It's just the lesser of the two rated devices. There are cases where there are combination ratings, okay, but we're not really discussing those today. Combination ratings for components, that is. Okay, let's next move on to the evolution of the UL standards and how that has impacted testing. So, the evolution of the standards, let's talk a little bit about the background of that. So first of all, customers must follow instructions by installing approved OCPDs. Okay, I'm probably going to say that a number of times, but it's very important. And we also know that most customers want to use common, inexpensive devices. We all want to do that, right? But UL, in contrast, requires us and other drive manufacturers to do destructive testings. And this testing has become more difficult in the past. And so what happens is the capabilities, the result, is often different between drives that are exposed and for the future. Let's talk a little bit about in the past that the drive manufacturers worked very hard to provide customers with these very desirable and forgiving compatibility from these devices along with the UL listing. Now, for existing product is grandfathered unless there are major changes to the product. But new product now, under the new UL testing requirements, it has many limitations. This new product does, based on installation type and the required short circuit current rating that customers need. So let's talk about the changes. First of all, UL 508C has been around for a long time, as long as I've been in this business. But as of February 1st of this year, UL is no longer accepting any new applications for UL 508C. However, they are allowing existing projects to finish. So you will see a few manufacturers, including Yaskawa, that continue to release new product under UL 508C. Okay. Now, existing product that's already been out there for quite some time remains valid and does not need to be investigated to the new standard unless UL-related changes are made to the product. And generally, that means something very significant. Okay. So for a lot of product that's out there, UL 508C is absolutely fine, and there's no concern whatsoever in using product that's listed to UL 508C. And even under UL 508C, there is this thing called component breakdown testing. Okay, and it's very severe kind of testing. One thing we have to do is short the DC bus itself, which is the rectifier, which does cause an explosion by itself. And then also the more severe test is the shorted capacitor test. And previously, UL allowed drive manufacturers to submit a letter from a capacitor supplier to say that this kind of failure was not a failure mode. Okay? Somewhere in the last 10 years, I don't know exactly when it was, so I'm saying approximately 2015, UL revised the requirement that this test must now be performed, and a letter from the capacitor supplier stating that it was not a failure mode was no longer sufficient. Okay, so even under UL 508C, in the last 5 to 10 years, the testing has become more severe. It's very important as we release new products, and that you may see some surprise differences between, say, for example, an A1000 and a G800. If they're both UL 508C, why did they have to have different rules for testing? That's because UL 508C evolved. Okay. So again, though, now the way of the future is really this new standard, which is 61800-5-1. That actually might look a little bit familiar to you, that number, because there is also a European IEC standard that that it's harmonized with. So you'll see an IEC standard with that number, and you'll see the UL standard. And they share a lot of the same requirements, but they are not exactly the same. So this was actually published all the way back in 2012. And we talk about component breakdown testing. Now, this component breakdown testing is even more challenging than 508C. Okay, even more challenging than the new requirement under 508C. And the biggest change there is that for products that desire to have a high FCCR rating, and I'll use the G800 as an example, which has a maximum rating of 100,000 amps. If we had tested that under 61800-5-1, we would have to take all of our products to a laboratory that was capable of supplying 100,000 amps and to use calibrated fuses. So it's gotten much more complicated under 61800-5-1. Okay, so let's talk a little bit about this component breakdown testing. As I mentioned before, we purposely cause shorts on the internals of the drive and see what happens. With different kinds of devices, whether it be breakers, conventional fusing, or semiconductor fusing on the input, and we see what happens. So the test result greatly depends on the actual construction of the drive, the amount of fault current, the available fault current, and the type of input protection, as I mentioned. So when a drive is exposed to a customer environment, this is most difficult because we wrap the product or the enclosure with cotton, and essentially the pass-fail criteria, which I'm going to talk about in a little bit, is that the cotton cannot ignite. But before we talk about that, I want to talk just a little bit about a simplified power diagram for a drive to get us all on the same page. Many of you have seen this before, but we kind of can think of the drive in terms of three power sections. One being the rectifier section on the left-hand side, and this just changes fixed AC into DC. And the next section is the DC bus, and generally consists of a bunch of bus capacitors to store and filter the energy. And then the last section is chopping up the DC bus back into variable AC to control the motor. And we're going to focus our discussion for the moment just on that center section, on the DC bus section. I'm showing a single capacitor there, but often there's multiple capacitors in series and parallel combinations. So let's talk about the shorted bus capacitor test. Now normally on a 240 volt drive, the rectified value of that is nominally around 325 volts DC. So when we apply a short across that, as required by UL, the capacitor loves it. He says, I have 0 volts, I love it, no problem. Okay, now why is that? Because these are 400 volt rated capacitors, and certainly it has no issue with 325 volts, nor does it have an issue with 0 volts, right? But let's look at a 480 volt drive, and this would be the similar to actually a 600 volt drive too. Now keep in mind that the 480 volt drive is using those same 400 volt capacitors, but in series. So normally it would be sharing the voltage. So when we short one of the capacitors, and this is what we're required to do by UL, put a short across one of the capacitors, again, that particular capacitor is very happy. Okay, but the capacitor that's connected in series to it doesn't like it at all, and the result is severe. Right? So again, 400 volt rated capacitors, you're applying 650 volts nominal typical DC to that capacitor, and it doesn't survive, and the event is severe. So let's discuss the component breakdown test just a little more. The test condition is such that we must surround the equipment under test with surgical cotton. When we're trying to determine the conditions for a drive by itself to pass the test, the cotton directly surrounds just the drive. But when we're trying to determine how the drive will pass when installed in a cabinet, the cotton surrounds the cabinet rather than the drive inside the cabinet. As we discussed on a previous slide, the purposely created internal short circuit is usually destructive. But destroying the drive does not mean it's a failed test. A test is considered a fail when the surrounding cotton ignites, when there is molten metal on the exterior, when a door or cover is blown off, when a ground connection is blown, or when a touch surface becomes live. Now this is most difficult to pass, either when the drive is mounted standalone by itself, or with its heatsink external for drives that have exposed capacitors. However, Based on the type of overcurrent protective device used, we also have solutions that will pass for these installation conditions. The following chart summarizes the typical results from many common installation types with different overcurrent protective devices. On the left side of this chart, from top to bottom for both voltage classes, you'll notice 4 installation types. Those being completely enclosed, 2 cases of enclosed with external heatsink, and also standalone where the drives are completely exposed. Across the top from left to right, we have semiconductor fuses, which are the fastest acting and offer the best protection. In the next column, we have conventional fuses such as Class C, C, J, or T, and these are also adequate protection in many cases. And then in the far right-hand column, we have molded case circuit breakers and RK fuses, which are the slowest acting devices and thus have more limitations of use. Now, based on what we have just learned about 240 volt drives, you'll notice there's only one case in which any of these devices won't protect a 240 volt drive, and that's the combination of a standalone drive with a circuit breaker or RK fuse. Even the 240 volt drive won't survive this, because besides the shorted capacitor test, there's also a shorted rectifier test that won't pass for this combination. Now, looking at the 480 volt and 600 volt cases, we can see there are a few more restrictions, and that's because of what happens when we do that shorted capacitor test on the 480 volt and 600 volt class drives. Notice that for the case of external heatsink for drives with exposed capacitors, that's the yellow cell in the rightmost column. Yaskawa does not recommend circuit breakers or RK fuses for protection. That's because we know the test result would not be good. For the new GA800 and GA500, our instructions do not prohibit it, but we still do not recommend. In the future, you are likely to see more conditions of use and instructions, not only from Yaskawa, but also from many drive manufacturers. Another area I want to point out is the yellow cell at the bottom of this chart. In most cases, conventional fuses will protect a standalone drive. However, some large drives mounted in this way must be installed with semiconductor fuses, and Yaskawa has special kits available for these conditions. Okay, I know that's quite a bit to take in, but remember this presentation will be made available for your reference. Now, one more thing before moving on. Please note that this chart is only typical, and not only must you absolutely pay attention to product instructions for individual products, but also differences across models within a single product family. So let's talk about the summary of the UL impact. Well, customers must follow the drive product instructions as we just mentioned when using these devices to protect a drive. And UL requires that the manufacturers do destructive testing. The test result is greatly affected by the choice of these devices. Again, 508C has become much more challenging. New projects have to use the new standard going forward. And then capabilities are becoming different between exposed and enclosed applications. So this again is just a summary of what we just discussed with regards to the UL standards. And another important point here on one of these previous bullets that I should mention is that we did mention that 508C products could be forced to get relisted to 5-1, and you also may see that Yaskawa pushes forward in getting what's presently listed as UL 508C, get them relisted to 5-1. Okay, so you may actually see that even though we are not absolutely required to do so. So anyways, to finish up with that, please pay attention to differences between products and individual drive ratings within a product. Okay, next let's talk about approved protection devices for the GA800 and GA500. And what those limitations are. So first of all, let's take a look at a couple different scenarios of enclosed versus exposed. And this is a little bit of review, but it puts it in perspective pictorially. So when a drive is not mounted in another enclosure, I'm calling that exposed. We can protect it with fuses, and the fuses that need to be used are listed in our instructions. So this is a thumbs up. This is okay. This is good. When we try to protect that exposed drive, not mounted in another enclosure, with just a molded case circuit breaker, this does not work when it comes to something that needs to be UL listed. Okay, and does something need to be UL listed or not? Yes, it does. According to the NEC, it has to be listed with another agency. And then, of course, if it's listed, it has to be used per the instructions. So this kind of scenario no longer works. We're allowed to allow that to protect a number of drives in the past, such as A1000. Now, is the fundamental design of the A1000 much different than the GA800? It is not any different. It's just that the rules for releasing a product are different now than what they were when we released the A1000 10 years ago. Even though both of these products are listed under and released under UL 508C. Okay, what about when drives are enclosed? Can we protect with fuses? And can we protect with circuit breakers? In most cases, the answer is yes, when the drive is mounted in the same enclosure. Conventional fuses, no problem. Semiconductor fuses, no problem. In most cases, molded case circuit breakers, no problem. How about when the drives are in the enclosure, but the overcurrent protective devices are somewhere else? The answer to that is yes also. These are both acceptable situations. However, there is an exception, and as I mentioned, as before, if we look at item number 2 there, when the fuses are actually semiconductor type, then they must actually be in the same enclosure. Okay? And the other thing that I had mentioned before is Yaskawa's position is that when a circuit breaker is protecting the drive, we want to see not only the drive, but the entire drive, including its backside, in the same enclosure if it has capacitors on the backside. Okay, so those are some exceptions. Okay, now let's talk about some let's kind of show that a little bit more pictorially of limitations of enclosed GA800. So just drives that are in another enclosure. The 240 volt situation is actually pretty easy because we have both fuses and circuit breakers when the drive is completely mounted in an enclosure. This is always a thumbs up, no problem. And for the 240 volts, even when the heatsink and capacitors are on the backside, this is no problem for the 240 volt drive. And I think if you think back to the prior explanation of those failure modes, remember that when we short the 240 volt capacitor, nothing bad happens. Or the capacitor on the 240 volt drive, that is. But when we move on to 480 volt, again, we have the drive mounted completely inside of the enclosure, and either fuses or a circuit breaker is absolutely acceptable. But then when we go on a 480 volt drive, and we apply fuses as the device, that's a thumbs up, that's good. But the circuit breaker, again, in the eyes of Yaskawa, and the same would apply for the 600 volt drive, is that we don't really like to see this as a protection method with heatsink external. Okay. Now the exception is that drives without exposed capacitors on the backside, and this is something that we will be clear about in our instructions as well. For those, you could actually do this with no problem, and your scout would have no problem. If, as a matter of fact, we will make our cabinet designs this way ourselves, that if capacitors are not on the back side of the drive, if that's not part of the drive design, no problem in having the heatsink external, even when using a circuit breaker for protection. Okay, so with that said, both the GA800 and GA500 have very detailed information on what can be used to protect the drive in what situations. So the best place to find that, because when we released both products, that being the GA800 and GA500, during the development of the product and the finishing of the instructions, there was not time to get complete information into the instructions, and we do go through a user manual revision cycle that, since we're a Japanese company, Japan is involved with that, and it takes a little time. So what we've done in the meantime is create some supplements for both the GA800 and the GA500. So what I encourage everyone to do is, instead of going to the manual, please go to these supplements to get the most up-to-date information. Eventually, we will have the same information in the manuals. But for the time being, please use these supplements as your Bible, if you will, for knowing what can and cannot be used for drive short circuit protection. Okay? And here's an example of the GA800. You can see that we show the use of semiconductor fuses. We show the use of what I would call conventional fuses, being class CC, J, or T, and also the limitations associated with using a multi-case circuit breaker or an RK fuse, which you can kind of think of as the same. In all cases, the maximum FCCR rating of the G800 is 100,000 amps, no problem, but there are conditions of use. In the case of a multi-case circuit breaker, as I mentioned before, that can no longer be your means of protection for a drive that's not enclosed, and we make note of that in the manual. So please be aware of that. And then we also make note of the mention that when using semiconductor fuses, it actually has to be in the same box as the drive. And we've got a nice solution for that as well. If you really aren't wanting to mount a drive in an enclosure, a big drive. And then we also have a similar document for the GA500. It has slightly different limitations. First of all, the GA500 is limited to 31,000 amps maximum SCCR. So that's an important difference. And then as far as the MCCB style that needs to use, it's actually very specific right now in the case of the GA500, and the specific type of MCCB that needs to be used at this point in time is called a current limiting type. So please read the notes on that. We always suggest a current limiting type of circuit breaker, but in the case of the GA500, presently, that's what it needs to be. But we are doing additional testing to hopefully remove that restriction in the near future. Okay, so let's talk about the impact on our Type 1 kits for the GA800. So first of all, as you may recall, if you're familiar with the GA800, it goes to very large sizes, up to 600 horsepower. Well, frames 10 and 11, 371 through 720 amps, Since the only thing that really can protect that drive in a standalone type of situation is the semiconductor fuses, we have made a special kit, a special Type 1 kit that actually is large enough to house semiconductor fuses. Okay, this is the only Type 1 kit that's available for these two frames of the 480 volt. And internally, it looks like this. It consists of the Type 1 sheet metal itself, plus some supports and bus bar for the fusing. Okay, now there's two actually. The customer must buy two separate things. That is, one is the kit itself that comes with the all the sheet metal parts and the supports and the bus bars. The fuses are purchased separately, so you can either purchase those from Yaskawa or from a third party. Okay, now let's talk quickly about the impact that this has had on the G800 packages. So I'm going to go through this pretty quickly because I do want to leave time for questions. But the G800 packages, which we released last November, is available in Type 1, 12, and 3R with a variety of options. Okay, in the cases of wall mount, some of these are heatsink internal, some heatsink external. In the cases of the floor mount, these are all external heatsink designs. So think about that for a minute, and maybe you'll think about what's coming next on future slides. So what we did is we wanted to prevent anyone from ordering only a circuit breaker to not be misleaded to think that that package was a protected package. So what we decided is that for any of those combinations with heatsink external, if you order a circuit breaker, you will automatically get fuses every single time for those particular combinations. Okay, so we make notes of this throughout our selection guide and throughout our price books. And I'm not going to ask you to study that now, but just be aware that in many cases, when ordering a circuit breaker, it automatically comes with fuses, and therefore you can't actually choose option F. Okay, it automatically includes it. Okay, now this is not the case for 240 volt because we all went through the 240 volt scenario, but it is the case for 480 volt, and we highlight in our tables where this is. It is the case, and it varies a little bit between Type 1, 12, and 3. It also varies between normal duty and heavy duty, so just please be aware of that. Okay. And in addition to that, we also try to clear up so that, because we are asking you to know what your available fault current is in the job you're trying to apply a package to. So we're helping you up front by listing for some very common combinations of our packages what the SCCR rating is so that you can make your proper selection on the front end. And so either you would have to overshoot and say, I always need 100,000 amps because I don't know, but that will be forcing you into a more expensive package. So the best thing is to know what the customer's available fault current is and match it up with purchasing a equipment that has an SCCR rating that is adequate but not overkill. Okay, so we try to help you with that by making note of that in our documentation. So let's talk about the key points to our session. Now that that actually completes all of our related topics for today, but I want to leave you with the following takeaways, the following key points. First of all, the equipment short circuit rating selection is very important and should be selected based on, again, available fault current, knowing what the available fault current is. The second thing is most drives require a separate overcurrent protective device according to manufacturer's instructions. And you will, of course, so please pay attention to instructions, and they are more detailed and more important than they were in the past. Next, UL approval has become much more rigorous, even prior to the new standard. Changing the way drives can be applied, such as enclosed or not, which protection device is chosen, what's required for short-circuit current ratio, voltage class, etc. Again, UL approval has become much more rigorous. UL 508C, again, those products remain valid indefinitely, and future products will be listed to the new standard, which a lot of us are just referring to as 5-1. And lastly, Euskalic strives to provide highly reliable and safe solutions with very clear documentation.
Okay, that concludes Steve's presentation and also the class today. And I want to thank you very much for attending. I'm going to stop the recording, and I wanted to